Hey, good afternoon, everyone. Let's get started. So today we are going to talk about long context large language model for efficient ML.ai. So long context is pretty interesting where you want to understand pretty long documents, and also you want to understand these long videos, multimodal models. So in order to save the memory, we will learn a lot of techniques to reduce the memory consumption to make it run faster for both the training and inference for long context large language model. So this is the agenda for today. We will first cover a recap of the context extension methods, like using rope, and then introduce long LoRa technique for training. We're also going to talk about inference evaluations for long context LLM, like the lost in the middle phenomenon, needle in the haystack, long bench. We also talk about efficient attention mechanism for long context inference, including the streaming LLM, dual attention, and query-aware sparsity. And finally, if we have time, we will talk about SSM, state space models. So let's start with a recap of the rotary positional embedding. So rotary positional embedding is a popular implementation for relative positional embedding. So each token not only have its own embedding vector, but also has the positional embedding. We've learned in the previous lecture, the rope basically chops the input into two segments and pair, and so that we can have an XY pair between the first element and D over 2 element, and that become a XY in the 2D dimension, and then we can rotate it by m theta. M is related to its position. Theta is a pretty large number, such that you can distinguish many numbers before you rotate it by 2 pi. Okay, and then we can see on the right-hand side, when we are doing the tension between Q and K, it becomes the multiplication of their magnitude and subtraction of m minus n of their angles. Okay, so the phase angle of the inner product of two complex vectors is actually the phase difference between the two complex vectors, m minus n. So the result is only related to the relative position m minus n. What if you want to extend the context window? So previously, this is the original theta. It can handle the context length up to 2K. What if you want to extend it to 4K? Okay, we should not just continue extrapolate. This is the unseen range, but instead we should double the frequency from every. Here we have this distance. We have 2 dots. Now we have 4 dots in the same distance. So basically, we are dividing theta by 2 so that we can still use the same range to represent the 4K range. So LLMs usually need to be fine-tuned after extending the context length, but fine-tuning under long context is pretty expensive. So how do we make it more efficient? So we introduce a technique called long LoRa. Just use a single GPU to fine-tune a llama 70 billion parameter model under long context. For example, this is a book, Harry Potter. Below is a section of the book. You give all the content right here. Now the book ends. Please tell me what high-level idea the author wants to indicate in this book. Altogether, we have about 30K tokens. If you feed it with the naive, the original Llama 2, which has 4K context length, which is much smaller than the 30K tokens, it will expect very poor result. Another work called the long llama, okay, used 128 TPU v3. That's a lot of compute, which is usually unaffordable. We'll introduce a technique called long LoRa, efficient fine-tuning. Fine-tuning a 70 billion parameter llama 2 to 32K context length, using only one node, okay, one node of 8 card, one node A100 GPUs. So let's see how that works. So under long context, what is the bottleneck? The attention is the bottleneck, right? Since transformers has two components, one is the attention that models the information across tokens. The other is the FFA layer that apply nonlinearity on the individual tokens, which is the bottleneck under long context. The attention, right? The attention is the bottleneck because the attention's computation complexity grows quadratically with the token length. So when the context length is pretty large, attention becomes the bottleneck. So how do we simplify the attention mechanism? Previously, we have to run the bottom triangle for the causal mask, right? But in here, we find it's enough for us to just do grouped, this kind of sparse, block sparse attention. They only, within this group of 4 tokens, these 4 tokens only attend to each other within this group. Similarly, these 4 tokens only attend to each other within the group, but not beyond the group. If we just do such block sparse, diagonal block sparse attention, that's problematic because these 2 groups will never talk to each other, right? So how do we solve that problem? We can actually shift the tokens, shift the attention mask by half, right? So therefore, these 4 tokens becomes 2 plus these 4 tokens plus these 4 tokens. So half of the head, we use this sparsity pattern. Half of the head, we use this sparsity pattern, okay? So what happens if we put them together, we will see these 2 groups, the red group and the blue group, they will talk to each other through the intersection right here, so since we are shifted by half. So now all the tokens can effectively talk to each other. If you stack multiple layers, if you stack just one layer, this red and this blue can talk, 10 to 10. And if you stack 2 layers, this red can talk to this blue, can talk to this red. So such information mingling can actually propagate as you stack multiple layers. So that's using this shift sparse attention to simplify the attention mechanism. Question. Because this is due to the shift. The blue part, there's a small triangle here, and there's the rest is shifted to here. That is a square because the part of triangle is right here, and here. Did you see a 2 by 2 triangle here on the top? It's overlaid. Another 2 by 2 here, triangle here, and the square becomes here. So the total area stays the same. So that's shifted sparse attention. And the second technique we find super helpful is to enhance the LoRa. We talked about LoRa in the previous lecture. We should also fine tune not only the layer branch, but also the input embedding and also the normalization layer. We've visited normalization layer many times. For example, in smooth quant and AWQ, we basically merged those scaling factors into the normalization layer, into the bias and also the scaling factor of the normalization layer. So here we are also tuning the normalization layer, not only tuning the LoRa branch, the low rank branch, but also the normalization layer, norm before multi-head attention, the norm before the feed forward, and also the input embedding layer. The fire here indicates that we are tuning that layer. So we avoided tuning this bulky FFA layer and also the multi-head attention layer to save the computation. Multi-head attention they are in parallel. If they are in parallel, how does so here we have multiple groups. So half of the head is like this, half of the head is like this. Each head is still individual. This is just one head. This is one particular head is like this, one particular head is like this. Right? This is not communicating between heads. This is communicating between tokens. So these 4 tokens and the second 4 tokens cannot communicate if you only have this sparsity pattern. This is within the head, just a single head, the first 4 token, second 4 token. And this is the other. This is the other pattern, which is these 4 from the 3rd to the 6th token, right? They are coming from the same 2K projection, right? So this is 1 to 4. This is 2 to 6. So this is put it more detail. How do we implement the sparse shifted attention? Okay, so we first group it by divided by 2, right? Half of the head and versus the other half of the head. In this example, we have 4. We have 4 heads, and here we have 8 tokens. We have 8 tokens, and we have 4 heads. We first split it by half, okay? Half of the head versus the other half, and then we shift half of the head. You can see the 1, 2, 3, 4, 5, 6, 7, 8 becomes 8. 1, 2, 3, 4, 5, 6, 7. Okay, and then we group it. Here, every 2 tokens are grouped together. We only do local attention within the group, and then the other half of the head, we do shifted attention like this. So this is during training. We run this shifted sparse attention, and at inference time, we run the full attention. So let's see how does that perform. Right? We are saving a lot of computation. Does it hurt the accuracy? So this is actually the perplexity. The lower, the better. So the blue one is the full attention. Well, long LoRa can pretty much match the perplexity of the full attention versus just using the LoRa. When the context gets longer, the perplexity will explode, showing that LoRa is not enough. And what about the training hour? The full attention can train up to 32 tokens. After that, it will be out of memory. Using LoRa can definitely shorten the training hours and can extend between 32 to actually 64K. However, you can see the perplexity of LoRa is pretty high. But long LoRa is right here, all the way to 64K tokens and remain the lowest in the training time. Here we did some ablation study to see whether it's helpful to remain only half of the remain P1. P2 here means attention head using pattern 1, all no shift, and pattern 2, all shift. Okay? If we don't shift versus everything shift does not perform as good as divided by 2 groups and cross the attention heads. Other sparsity technique like dilation, block sparse, and stride sparse across the head doesn't perform as good compared with the S2 attention. And in particular, the lowest perplexity is achieved when we are testing with full attention. Okay, training with shifted sparse attention, but test with the full attention. And then let's see how does the enhanced LoRa work, right? We also tune the input embedding and also tune the normalization layer. These 2 are very cheap to tune. For example, the normalization layer has very few parameters. We have very limited additional cost. Normalization layer 0.004%, embedding is 2%. But compared with full fine-tuning, naively using the LoRa, as you increase the rank, the perplexity still remains pretty high, like 3 points higher than the full fine-tuning. If we add normalization tuning, it becomes a little better, 1 point. And add both normalization and embedding tuning, it becomes pretty much matching the original full fine-tuning's perplexity. And here we are using very low rank, just 8. compared with even using LoRa, if you use 256, still doesn't work. But here we just use a rank of 8 plus normalization, embedding fine-tuning. It can work as well as full fine-tuning. So let's try it on a few scenarios. So this is the passkey retrieval task. What is passkey retrieval? So this is a very, very long document. And we insert a passkey 12362. Remember it, 12362 is the passkey. And then we have a lot of unrelated text. The grass is green, the sky is blue, the sun is yellow here. Here we go. Repeated several times. And then finally we ask, what is the passkey? The passkey is, and try to see if we can correctly output this 12362 as the result. So using the original Llama 27B, which has 4K context length, the passkey retrieval accuracy drops very quickly, almost to 0 after 4K context length. But after using long LoRa, we can extend it to 32K. And if we extend the positional encoding, we can all the way go beyond 40K. Okay, very effective to extend the context length in the passkey retrieval task. Okay, so let's see, how do we evaluate the performance of long context LLM? So let's first introduce the popular loss in the middle phenomenon. So the loss in the middle phenomenon is saying that the accuracy is pretty high in the beginning and in the end, but the accuracy in the middle is pretty low, right? So very high accuracy when the relevant information appears at the start or the end of a context, but very low accuracy when the relative information is in the middle of the text. And the key insight is that a very fluent long context response doesn't imply you can remember the stuff. It's highly possible the language modeling perplexity is pretty good, but you're forgetting the things in the middle. Therefore, perplexity is not enough. We need more rigorous evaluation to understand the capacity and performance of long context LLM. So we'll introduce two benchmarks. One is needle in the haystack. The other is the long bench. So needle in the haystack is a pressure testing for large language models under the long context. How does it work? So we have two axes. One is the context length from 1K, 10K, 20K here to 128K. And the y-axis is where do we place the needle in the document, okay? So this is start of the document. This is 25%, in the middle, 50%. This is 75%. This is in the bottom and in the end of the document. Where do we place the needle? Now we can see if the screen is showing that you have 100% accuracy to retrieve that needle in the haystack. Yellow means you have 50% accuracy, and red means you have 0% of accuracy. And we can observe when the context length is pretty short, like 1K, 10K, 20K, everything is green, right? You can retrieve very accurately in the beginning, in the middle, and also in the end, right? However, as the document gets longer, the accuracy is becoming worse, starting from like 73K. The very beginning accuracy is still pretty good, like 100%, right here. But in the middle, like 25% to 30%, you have 0% accuracy of retrieving your passkey. In the later part of the document, the accuracy returns to 100% again. Okay, so that's the loss in the middle problem begins to appear. It gets even worse when the context gets longer, like 128K. Even at about 75%, you get only 65% of accuracy of retrieving that passkey. So in short, this needle in the haystack has basically inserting the information, we call it the needle, okay, at a different depth of a long context document, of a long document, like we call it the haystack. Right? This is a smaller haystack, only 1K. This is a larger haystack, 128K. Right? A similar example of needle could be something like the best thing in San Francisco is eating a sandwich and sitting in the Dolores Park on a sunny day. Okay, and then we ask the model at the end of the document, at the end of the haystack, to recall the information, which is the needle. What is the best thing to do in San Francisco? And I should answer to eat a sandwich and sit in a Dolores Park on a sunny day, right? To find this needle in this long document in this haystack. Another benchmark is called the long bench to evaluate the long context capability more comprehensively. The needle in the haystack is still artificial synthetic benchmark, right? But this is more real world a real world data set. For example, include different tasks like question answering, summarization, few shot learning, the English and Chinese, and support context up to 13K tokens, which is still not quite long, but with automated evaluation metrics. And it can consist of not only synthetic data, but also code data, single document QA, multi-document QA, summarization, few short questions. And the key finding is that techniques like the scaled position embedding can improve the long context understanding. The techniques like context compression and retrieval can help, but not as effective as models inherently designed for long context. Given those benchmarks, let's see how do we improve the inference of long context large language models. Let's first recap the concept of KV cache, which we learned in the previous lecture. The KV cache grows linearly as the number of tokens increase. So it's multiplying the mini batch size, the number of layers, number of KV heads, the dimension of the embedding, the length of the sentence, K and V, two elements, and the precision. Okay, so it's 2.5 megabytes for each token in the 70 billion parameter model. Okay, when the batch size is 1, sequence length is 512, is 1 gigabyte. A batch size of 16, sequence length of 4K, that's 160 gigabyte, like 2 100 GPUs. And this KV cache size will grow linearly with the batch size. Okay, sometimes even easily outperform, easily surpass the model size. Okay, so we'll introduce 3 techniques to solve this problem of large KV cache size. Well, the first technique is streaming LLM and attention sync. Second technique is dual attention. The third technique is quest, query aware sparsity. So let's talk about streaming LLM for long generation in streaming applications. So we need large language models in streaming applications, such as multi-round dialogues, where you want to continuously interact with a chatbot non-stop. But this is very challenging because long conversation require extensive memory consumption during the decoding stage. For example, using the transformers, using the original transformer, the memory will grow linearly with respect to the number of tokens. Okay, so the x-axis in here is the input sequence length, and the y-axis is the perplexity versus the memory. Okay, so the memory will grow linearly, but the perplexity will stay good in the orange curve until 4K, which is the Llama 2 when the Llama 2 is trained. After 4K, the perplexity will explode. Okay, it no longer works. Another work using the windowed attention doesn't solve the problem either. It solves the memory problem where the memory can stay constant using the windowed attention, but the perplexity will explode as in the green curve. It will explode as soon as the first token in the window is evicted. So our TA Guangxue developed a technique called streaming LLM that can handle this problem. Okay, so without streaming LLM, after a while, the model performance will break. But with streaming LLM on the right, you can continuously interact with the chatbot non-stop. Finally, the non-streaming LLM will get out of memory as the conversation gets long. So how do we prevent either model performance breaks and also prevent the model to run out of memory? So let's visit a few techniques. For example, if you want to keep a constant memory, an actual thinking is rather than using everything in the KV cache, can we just remain the local tokens in the KV cache and use a windowed attention? Only keep the most recent tokens. Only keep the most recent, like in this example, the most recent 4 tokens in the KV cache. So here we have our cached tokens, but you can imagine the perplexity will be very poor. It will become very poor perplexity as soon as the first token in the KV cache is evicted, when the text length surpass the cache size. So here we actually see 2 failures. One is when using the windowed attention in orange, when the input length is longer than the KV cache size, where the first token is evicted, the perplexity will explode in orange. The second failure case is the dense attention, the blue part, when the input length exceeds 4K, which is a pre-training length, the perplexity will also explode. What about other techniques like dense attention? Of course, the efficiency is poor. It requires ON square complexity for the efficiency perspective, and the perplexity will also explode as the size will exceed the training context length. We talk about windowed attention, although the memory is good, but the perplexity is pretty poor. We can also, using a sliding window with recomputation, the perplexity stays pretty good since we are just get rid of the KV cache and recompute every time, but the compute is all TL square. L is the length of the recomputed tokens, and it's quite unaffordable. T is the total number of cached tokens. So we observed an interesting phenomenon called attention sink phenomenon, where starting from layer 2, the first token is very heavily attended. So this is the attention map. The first token is all red. Similarly, for the other layers and other head, the first token is all red. It's very heavily attended. Why is that the case? Because we are using the softmax and make sure for different tokens, the attention score needs to sum up to 1. Even if some of the tokens does not need to attend to anything, they still need to sum up to 1. So they need to dump the attention score to some of the tokens. And the first token is globally visible due to the autoregressive nature of the generative model, right? So the model decided to dump those redundant token attention score into the first token, which is right here. The first token received very heavy attention score. Very interestingly, we observed this phenomenon like 3 years ago, back in the 2021, the SPATM project, sparse attention project, but we were not able to explain it at that time. For example, in this sentence, he is a very famous researcher in the computer architecture area and published many papers. We find it attend very heavily to the first token right here. That's not just a single case. That's actually appeared in GPT-2 in 2021. This is several other examples using GPT-2 for language modeling. Like Du Fu was a great poet of the Tang Dynasty, etc. We find many tokens can be safely pruned, like Fu was can be safely pruned, but Du, the first token, can never be pruned, which is very interesting. And later we find the first token is the attention sink, which should not be pruned. So this is the rationale behind the attention sinks, where the softmax operation basically let everything sum up to 1. So you need to dump those redundant stuff in the first token because it is globally, like this sentence where it's globally visible to all the subsequent tokens because of the autoregressive modeling. Okay. And we naturally ask the question, the first token is very important. We call it attention sink. Is it due to their position or is it due to their semantics? So here we did an experiment. The window size here is 1K. If we have 0 attention sink token, the complexity will explode to 1,000. If we have 4 attention sink tokens plus 1020 window, the perplexity is getting normal. But if you insert 4 line breaks, they have no semantic meaning, plus a window of 1020, the perplexity still remains pretty low. Okay, so we find adding initial 4/n, these line breaks, can also recover the perplexity, which is super interesting, which is showing it is the position that matters, okay, not the semantics. So what should we do? Given the attention sinks, we should preserve the key and the value of attention sink tokens. Never evict them from the KV cache. Right? Just always have these yellow attention sinks in the KV cache. And then we keep a sliding window for the later tokens 4, 5, 6, 7, 5, 6, 7, 8, 6, 7, 8, 9, using such a windowed KV cache. One thing we need to pay attention to is the position encoding. Okay, we should use the positions in the cache rather than in the original text. This is the position in the original text: 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is the position in the cache. So from 3, we directly go to 4 rather than go to 6. So that's something we need to take care when we're implementing that. We talk about the page attention. So how should we implement streaming LLM in page attention? Actually, we just always pin the first KV page during the page attention, right? Since each page is roughly 16, 32, 64 tokens, the simple implementation could be quite simple. We just always pin the first page in the KV page. So let's see the comparative performance. So the dense attention, which is in blue, it will fail. The perplexity will explode beyond the pre-training attention window size, like 4K for Llama 2 models. But the window attention, which is in orange, it will explode after the input exceeds the cache size when the first token, which is the sync token, is evicted. Well, streaming LLM in red shows very stable performance. I'm very close to the sliding window with recomputation baseline. And here we tested all up to 4 million tokens, still didn't show any failure. It might be even longer, but we didn't test it. Efficiency-wise, we compare with the only working version, which is recomputation. Without KV cache, actually, we find that the lengths get even longer. The speed up is getting larger. Actually, the more you generate, the more you save. And here is comparing the memory. Okay, so streaming LLM has consistently lower memory and faster speed. here we ablate how many attention sinks do we need? Why do we need 4 attention sinks? So we tried 0. Of course, it doesn't work. The complexity is too big. 1, 2, 4. We find, for example, 11 to 7b, from 11 to 10 to 9, 4 is a sweet spot. After increasing the number of sinks to 8, it doesn't help much. So 4 is a very practical number of attention sinks. Yes, that's very related. Actually, that's the next slide. So what if we apply a dedicated learnable token to the beginning, right, of a sentence? No matter if it's language or it's image, we apply a dedicated learnable token, introduce an actual learnable token at the start of all the training samples, and let's see how that works. Actually, using this learnable sync, okay, compared with the vanilla model, just using a single token, the vanilla model has 18.49 perplexity versus the learnable sync has 18.01. Okay, it's performed quite good compared with using the vanilla without the dedicated attention sync, and we no longer need 5 or 4 syncs. Here we just need 1 learnable sync. So when you are training the model, you can insert this attention sync. And let's see, for the vision model, people also find these sync tokens, like right here, these colorful dots. These attention syncs emerge in low semantic background pixels. So the bird is this insect is in the middle, but in the background, low semantic background pixels, we observe a lot of attention syncs. And similarly for the BERT model, okay, the bidirectional BERT model, attention syncs are those separator tokens at the end of all the sentences. Like in the end right here, it's very red. So VIT and BERT model, those encoder models also have attention syncs. But streaming doesn't equal to long context. For example, we design this experiment, have a query, have a register for line 0 is something for line 10, for line 20, etc. And then we ask the register containing line 0 is, we try to retrieve 8806. And then we keep adding new contents and try to look back to ask the content. And we find actually when the cache configuration is like the cache has 2044 plus 4 sync tokens, when the token distance, this is the distance between the query and the token, okay, and the needle. So when the token distance like 2300 exceed 2048, the accuracy goes to 0. And when the cache is 4K, but the distance 4.6K right here, the accuracy will also drop to 0, okay? Because the content is evicted from the KB cache. By no way you can retrieve it. So let's see, how do we solve this issue? Let's take a 5-minute break. Then we are going to talk about dual attention and query-aware sparsity to solve this issue. Let's continue with dual attention for long context large language model. So dual means 2, right? We have 2 kinds of attention heads. One is the retrieval head, one is the streaming head. And let's see how do we exploit these 2 kinds of head to improve the efficiency of long context large language model. So the problem here we want to solve is long context problem. We want to understand long documents, long images, long videos. For example, one input image, 224 by 224. Nowadays, we can convert it to 256 tokens using clip or cyclip. using that for 1 hour long video sampled at 1 frames per second, that equal to roughly 1 million tokens. So we need to efficiently handle those long context LLM to handle long videos, high resolution images, and long documents. However, with only 80 gigabyte of memory, nowadays this Llama 3 8B decoding can handle up to 500K tokens. Beyond that, like 600K, it will get out of memory. Okay, so this is latency, this is the memory. Beyond 500K, the memory is more than 80 gigabytes. But this dual attention mechanism can handle here all the way to 1 million tokens. Actually, we tested all the way to 3 million tokens if you combine that with KV cache quantization. And also, it gets very significant speed up. Let's see how dual attention works. So the challenge we are trying to solve is, one is the memory bottleneck, one is the decoding latency, right? So storing all the KV states across all the heads will consume massive amount of memory, right? So like 137 gigabytes for 1 million contacts in Llama 3 8B. The other is the decoding latency, which grows linearly with the sequence length. And some of the existing KV cache compression technique, like H2O, streaming LLM, TOMA, will damage the long context capability, like we see in the last slide. So to solve that problem, the dual attention accelerate both the pre-feeding and the decoding, reduce the KV cache size, and preserve the long context performance. So on the left is the full attention, on the right is the dual attention. Okay, almost half the GPU memory, 78 gigabyte versus 49 gigabyte. And the total time is also halved for the pre-feeding stage from 4,000 seconds to 2,000 seconds. And here is at the decoding stage. Okay, so each token with full attention require 864 milliseconds. Now is halved as well, almost 2x speed up for both the encoding stage and also the decoding stage. And we can fit up to 3.3 million tokens in the context. That's roughly a 3-hour video, okay, sampled at 1 frames per second, so we can understand the whole movie. And let's see how that works. Let's first observe the attention map and see what are we actually attending to. So there are roughly 2 kinds of heads. Okay, so the sentence here is the best fruit is orange. What is the best fruit? Orange. Okay, so the first kind of head, the attention is we pay attention anywhere. For example, we have 3.1, 2.9, 4.7, these 3 dots near best fruit in orange. Okay, so we call them retrieval head. So you can capture the information between the generated token to any of the previous tokens. Okay, versus the other kinds of head only attend to itself, the local tokens versus the first token. You can see it's very similar to the streaming LLM's pattern, where only the local tokens and the first token is attended. Similarly, for other similar token like this, none of the things in the middle is attended, versus for the streaming head, you can densely attend to anything in the middle. And then what if you try to prune some of the heads? Okay, so if you try to prune if you try to prune the retrieval head, the accuracy will drop very, very quickly. Okay, the accuracy drop like 20. If you prune 20%, the accuracy goes to nothing. But if you prune those streaming head like this is the streaming head, the accuracy will stay pretty much unchanged. And if you prune randomly, that's something in between. So the insight is that not all the attention head need to do full attention, attend to everything. Okay, but we can categorize all the heads into 2 groups. One is the retrieval head, which is the original dense attention, okay? Focus on important tokens from earlier tokens in the sequence. Basically, anything can attend to anything. The other kind is the streaming head, which only focus on the recent tokens and the attention sync tokens, okay? It only need a very small KV cache. The size equal to the number of the attention sinks, which is roughly 4, and also the recent tokens, which is constant. No matter how long your conversation goes, the window of the attention of the streaming head stays the same. So the solution of dual attention basically apply the full KV cache to the attention head and use a very lightweighted, constant size cache for the streaming heads. Okay, so this is the retrieval heads KV cache, which grows linearly with the sentence length, token length, versus the streaming head only keep the sync in yellow and the most recent tokens, which is constant size of the KV cache. And let's see how do we train the alpha so that we can determine whether a head belongs to attention head, streaming head, or the retrieval head. Okay, and we expect the algorithm should be very simple, right? Such that we can train it using just a few GPU hours, hopefully just one GPU, right? So here the algorithm is very simple. We train using both the full attention and streaming attention, but mingle them together with the learnable parameter, which is alpha. Okay, so assign a trainable gate to each head. Okay, and then the gate of alpha will blend the full attention and also the streaming attention, allowing the model to learn which heads are necessary, should be the full attention versus it could be a streaming attention. So here we get alpha times full attention plus 1 minus alpha times the streaming attention. But this is the full attention. The difference between full attention and streaming attention is the mask. Full attention uses the causal mask. Streaming attention uses this lambda-shaped mask. And then we try to distill them by minimizing the difference between using everything uses the full attention versus the mixture of this combined version using still attention. Okay, and we regularize them by making those alpha small and try to add these losses together with distillation loss and regularization loss. So how many parameters do we need to train? So for example, for Llama 2 7B, we have only 32 layers, 32 head. We need 1 alpha for each layer, for each head. So altogether, there's only 1K gate values that need to be trained. And that can be completed just in a few hours in one node, 8 GPUs, 8 A100 GPUs. And how do we train that? We design a task. So right here, the training example is a lot of long paragraph followed by remember the sentence of words is the first passkey to the vault. Lima Zulu Golf Papa, say something random as the first passkey, and then we have this second, fourth, all the way to 10th passkey. Right here, we want to retrieve what is the first to the 10th passkey and add the loss to Lima Zulu Golf Papa, etc. Okay. And here we show 32 layers, 32 heads. We have 1,000 altogether, 32 by 32 gates. What is the value of the gates? If the gates is blue, it's very small, we can prune them away. And that is streaming head. If it is red, showing alpha needs to be pretty large, then they need to be the full attention head, or we call it the retrieval head. So what about at inference time? We can set a threshold. Okay, if alpha is greater than the threshold, it is characterized as full attention. You need to do the full attention mask. Versus if the alpha is smaller than the threshold, you can keep it as a streaming head. Okay, streaming head, the attention map is lambda shaped. Only recent and sync token, the KV cache size is constant. So what about accelerating decoding versus the pre-feeding? So this is accelerating the decoding part. We have 2 kinds of KV cache. One is the retrieval head, where we need to store the KV for all the tokens. The other is the streaming head, where we only store the yellow attention sync and the most recent tokens. Therefore, it consists of only constant memory. And when we are doing the computing, we split them into retrieval and streaming head, and output of both heads are concatenated for the final projection, QKBO, the O projection. So this is the decoding part. What about you during the prefeeding stage? So in the prefeeding stage, we implemented a chunk prefeeding to split the sequence into fixed length chunks. Okay, so this is the first chunk, second chunk, third chunk, fourth chunk. Okay. So what is the time complexity without using dual attention? We have to calculate the area right here in the triangle, which is L squared, right? But now with the attention, attention streaming has, we need only constant L times K time complexity, okay? Because here we are keeping the most recent token, which is blue plus red, which is constant size of 6 in this case. So the time complexity is reduced from OL squared to OLK. What about the memory complexity? That's the size in the length of the KV cache. Previously, it's L, grows linearly with the number of tokens. Now it's fixed, it's K, only the first attention sync plus most recent tokens. So time complexity is the area of this triangle, and the memory complexity is the size of the X dimension. Okay. So that's where the saving is coming from. And let's see, in practice, how much of the attention has could be categorized as streaming head. The more the better, or the lower the better. The more streaming has, the more we save, right? So we hope the percentage of streaming head could be as high as possible. So the conclusion here is roughly 40%, 50%, like half of the KV cache, half of the heads is categorized as a streaming head. So actually half of them you can have roughly a negligible KV cache size because they're constant. And then recent token, when the total size is long, the KV cache size for the streaming head is pretty low. What about the accuracy? So this is needle in the haystack. This is a long bench, needle in the haystack for this is llama 2, this is llama 3 on the top and bottom. For baseline methods, like full attention can be green everywhere, but H2O fails, streaming LLM fails, TOBA fails, FastGen fails, but dual attention can perform very well. Okay, so even 25% of the heads are this retrieval head, showing that you are pruning away 3/4 of the heads to be streaming head, because llama 2 is MHA versus llama 3 is GQA. You can prune away half, right? You can prune away half. And here is showing the accuracy on the long bench when the sparsity is 50%. The KV cache sparsity is only 50%. The red line still maintains the same as the baseline. And similarly for short context benchmarks like MBPP, MMLU, MT bench, under 50% KV cache budget, the accuracy stays quite well on these benchmarks. And let's see what is the speed up and memory saving. It can provide about 2x memory reduction for MHA, 1.6x for GQA model. Okay, why higher for MHA and lower for GQA? Because for GQA, you have less number of heads for the K and V, right? You are sharing a lot of heads to share the same K and V, so the number of heads is smaller. And it's harder to prune since you have to have exactly multiple heads are sharing the same KV head. So previously, using the baseline method, you ran out of memory roughly at 500K context length, but now you can go all the way up to 1 million. 500K is like a half an hour video. 1 million, you can now understand one hour of video. So this is the pre-feeding memory and the latency improvement. This is the decoding memory and latency improvement. So for the pre-feeding, it's about 1.7x latency reduction for MHA and 1.6x for GQA model. Memory saving is about more than 2x versus 1.5x for different benchmarks. So natural thinking is, what about if we combine that with KV cache quantization? Okay, so dual attention is, you can think of it as pruning and sparsity. We can remove lots of the attention scores. If we combine that with KV cache quantization, it can work super well. So by quantizing the weight to 4-bit and KV key in the value to 4-bit, we can fit 1.8 million tokens in a single A100 GPU. Okay, if we combine that with 4-bit KV cache quantization, which we talked about previously using QServe, 4-bit KV cache, we can further boost it to 3.3 million tokens. That's like a 3-hour-long video, which is pretty cool. Okay, so that wraps up the dual attention for long context large language model inference. We can accelerate both the pre-feeding stage and also the decoding stage using two kinds of KV cache. One is the streaming head, one is the retrieval head. So let's talk about another technique. Let's talk about Quest, query-aware sparsity, to accelerate long context large language model. So 3 years ago, we find the sparsity appears naturally in large language model. For example, in the sentence, I bet the video game is a lot more fun than the film. Okay, so these are the keys. Some of the tokens receive a lot of attention, like video and game, is heavily attended. But some of the tokens, like across different tokens, they are not very heavily attended. So the cumulative importance score is pretty low. And so we can safely remove these tokens, which is showing that the KV cache has a lot of redundancy. We don't need to keep all the tokens in the KV cache. So sparsity appears in KV cache, but previous efforts have some limitation. For example, compared with the dense attention, they keep all the contextual tokens, which is pretty memory intensive. You have to grow the KV cache linearly with the context size. Some query agnostic sparsity, like fixed pattern sparsity, like streaming LLM, like H2O, once a token is evicted from the KV cache, it can never come back. If it is gone, then it's gone. Okay? So we keep the token based on past information. If this token is not important here, it will never be important in the future. Similarly, for this token, once it's pruned based on the previous information, when future tokens comes, it will never recover. So although it solves the memory issue, but the accuracy is pretty low. But query-aware sparsity basically says the sparsity pattern should be dependent on which token you are currently decoding. Okay, so an evicted token can still be attended by future tokens. For example, this token, the second token, at this time step, it is evicted, but at the next time step, it can recover. So it can save both the memory and also keep a very high accuracy. So that's the idea of query-aware sparsity. So the sparsity of the KV cache, the sparsity pattern of the KV cache should be dependent on the new query token which you are decoding. So let's see example where why query-aware sparsity is crucial. In this sentence is A is B, C is D, A is. Upon this moment, A is B, C is D, token B is not critical at this moment. You see the attention score associated with token B very blue as of this moment. But as you continue to go deeper, A is, B suddenly becomes very important because the result should be B. You should decode, the next token to decode is B. So although previously, at this moment, B should be evicted based on the cumulative attention score. But at this moment, should be reside in the KB cache. You cannot prune it. Okay, so which shows the criticality of the dynamic pruning is very important. It's highly dependent on the input query vector Q rather than static. So what Quest does is using this query-aware sparsity in the attention mechanism. So we keep everything in the KB cache. So we don't save the memory capacity, but we save the memory data movement. Okay? So we only fetch those KB pages if it is important. Otherwise, we keep it in the memory, but we don't fetch it. So how do we do that? When a new query comes right here, this is 1 by D. D is the hidden dimension. In this case, it's 8. So we have many KB pages. At each page, we may have like 16 tokens. 16 tokens actually is 4 in this case, but actually it might be 16 or 68 or 64 in this dimension. This dimension is a hidden dimension, 8 in this case. 2 colors indicates K and V. Okay, first page, second page, and nth page. As the sequence gets longer, you have more pages. So we try to compute which page is in the KB cache is crucial. If it's not crucial, we should prune away some of the KB pages, right? Then how do we prune it? A golden model would be you just multiply the query with each key and see which one is promising. But that testing is just too computation heavy, right? You already did all the computation, then even if you prune it, it doesn't save you much, right? So a smarter idea is to find some representative key and value, key actually, for across this entire, these four tokens. Actually, this example actually is 16. Across these 4 tokens, we find element-wise min key and element-wise max key. Okay, so the large dot product can only happen if this query is dot product with this min key or this max key. Okay, so this is the element-wise product with the min key. This is the element-wise product with the max key. And then we find the max between the min and the max right here. So the red one is the largest value. Okay, and we sum it up. So rather than doing a dot product with every entry, like 16 entries, we only dot product with 2 entries, the min and the max, element-wise min, element-wise max. And finally, we sum it up as the number to represent the importance of this whole page. Okay? So this page is large, this is large, this page is small, then we can prune away this page. It still resides in the memory, but we don't fetch it from the memory. So reduce a lot of data movement. So this is how we put it in code. When we are inserting a new token in the KB cache, we first find the min key and the max key. Okay, finding the min and max. When we are performing the self-attention, when the query comes, the query will be multiplied dot product with the min and the max, okay, and then find the max between them to see whether this page is important. Okay, let's see how that performs. So this is 10K versus 100K passkey retrieval. This is on long chat. This is on Llama. It's the first part versus the second part. We can see the Quest can achieve almost perfect accuracy with a cache size of 60 all the way to 64. And when 512 is 100%. It still remains quite good despite these baseline models like H2O, TOA, StreamLLM completely fails, only 1% accuracy for the passkey retrieval. This is 10K, this is 100K. All the way to 64. And when it comes to 32, that's too small. Okay, that's too small, it still drops to 65. And for 100K, a longer passkey retrieval, originally you need 100K, but now we give it only 4K. Okay, 4 over 100, that's very small budget. Okay, you have 100%, 2K still 100%, 1K slightly dropped 96%, although baseline almost go to 1%. And with 256%, that's 256 tokens, that's too low, we get a 88% passkey retrieval accuracy. So this is 4K out of 100K. That's like roughly 1%, which is 1K over 100K. That's roughly 1%. You still get 96% of accuracy. So this is the language modeling result, comparing several methods like TOA is very high, full attention is in green, fast is in red, H2 is in blue right here. So as the input length gets longer, the perplexity remains low. Very closely match the performance of the full cache model. So this is the result on the long bench, which is a 32K long chat. Okay, and we give it only 2K tokens out of 32K. Okay, so a budget of 2K tokens can achieve comparable performance as the model with full KV cache. Similarly, right here, we have only 2K cache budget, 2K cache budget, and more results. What about the efficiency? We don't save the memory, but we save the data movement. If the KV page is not promising, we don't load it from the GPU memory. So it can accelerate since data movement is expensive, both energy-wise and also latency-wise. So this is for different sequence length. So this is 8K, this is 16K, this is 32K. And the budget is the same, it's 2K budget. And we can imagine the longer the sequence length, given the same budget, the larger the improvement, okay, from 1.7 to all the way up to 4x latency reduction compared with the full cache. This is in the logs, this is in the linear scale. And the latency contains two parts. One is criticality estimation, and then top K filtering, and then the approximate attention. So actually the criticality estimation consumes larger overhead, which can be alleviated by sharing the criticality across multiple tokens. So like Q1, Q2, Q3 can share the criticality with Q1, okay? So in that way, you can save the criticality estimation to amortize the criticality estimation. Or you can reuse the criticality estimation in layer 1, reuse it for layer 2 and 3, and maybe do it again in layer 4, etc. to alleviate the proportion of this light blue part. So this is the end-to-end latency, about 2.2x, when the sequence length is 30 and token budget is 2K. And this is showing the P16 weight versus showing that this is compatible with 4-bit weight. So this is more results for efficiency comparison. Baselines need nearly full KV cache to achieve lossless performance, and Quest can use a much smaller KV cache. So this is the average context length. This is the attention latency. Attention latency, so Quest is showing as the lowest across different benchmarks and require the lowest context length budget compared with baseline methods like full attention, TOA, and Quest. All right, so in summary, we talk about Quest, query-aware sparsity to filter out which KV page is crucial. So there's a lot of redundancy in the KV cache, so we can use the query-aware manner to dynamically determine which one can be skipped. Next, I'm going to quickly talk about beyond the transformers. What are some of the non-transformer architectures that is efficient, starting from state space models. So in the attention, roughly you have two tasks. One is to compute the information between the tokens, and then the other is the transformation within a token. Okay? So the state space model, it can handle the sequence communication as another alternative as this multi-head attention mechanism. So it's very similar to RNN except that there's no nonlinearity right here. Okay. So there are three matrices. One is A matrix, which controls the state transition from T-1 to HT. And the B matrix basically map the input to the hidden state. And C maps this hidden state to the output. So just using this naive state space model, you can expand this equation such that you can represent it by a convolution. It's very simple to implement. And the new work, the Mamba, which introduced the selective state space model. So rather than without any selectivity, different tokens have the same importance. With selectivity, it can allocate a different importance to different tokens. Like I want to order a hamburger. Hamburger is given a lot of importance. And that is achieved by tweaking the A, B, C and make them input dependent. Okay, so these A, B, C matrices are also the function of the input X. So that creates a problem. Previously, since you have no nonlinear function and ABC is constant, you can expand H1, H2, H3 recursively and actually implement that in a convolution very easily. Okay, so linear occurrence can be implemented with global convolution. However, the selectivity, the ABC will change depending on the input, so it can no longer be implemented by convolution. So how do we solve this problem of slow training issue? Luckily, the parallel scan is one of the implementation we can borrow, similar to computing the prefix, like 4 plus 1 is 5, 4 plus 1 plus 5 is 10, 4 plus 1 plus 5 plus 3 is 13. So this is the prefix sum, calculating the prefix sum is a very classic algorithm that can be implemented efficiently by parallel hardware using the parallel scan algorithm. Calculate the first 1 and 2, 3 and 4, and the 1, 2, 3, and 4 in a parallel manner. So we can do that similarly for computing the hidden states in Mamba. Okay, compare to compute 0 and 1, 2 and 3, 0, 1, 2, and 3 all together, parallelize them using the compute in space rather than serialize them in time. And later, there are several hybrid models combining the transformer layer versus the Mamba layer, even the MOE layer. So by stacking them together, so you have several Mamba layers, several Mamba MOE layer. So some of the FFN becomes mixture of expert. We talk about that. Some of them is using transformer. Some of them is using the MOE version of the transformer. And you can do architecture search to stack different components. Actually, this model can fit a single 80 gigabyte of GPU to support 256 tokens. And the advantage of this Mamba or state space model is that you have a fixed amount of KV cache rather than linearly growing KV cache. All right, with that, here's a summary of today's lecture. We talked about long context, large language model to handle long documents, high resolution images, and also long videos. We talk about long LoRa to fine-tune efficiently long context models, and also introduce several benchmarks like needle in a haystack. We talk about streaming LLM, dual attention, and quest to exploit sparsity in the KV cache. Finally, beyond the transformers, we briefly introduced the state space model with constant KV cache size.